Okay, today is about conditional probability. If I put some conditions on it, it's sort of like this. My kid asks to use the car, and I say, okay, 2 conditions. Got to be home by 11, and you can't have any more than 2 friends come with you in the car. Okay, those are conditions that I'm setting. All right, conditions in probability is kind of like that. So hopefully, by the end of the hour, we're going to make sure that you understand how to use a tree diagram to do that conditional kind. When you go to an animal shelter, would you agree that dogs are generally more popular than cats? They are. When I've done surveys, the vast majority of kids prefer dogs over cats. Not that they hate cats necessarily. Some people do, but generally dogs are more preferred. So this one's probably pretty right. When you go into the dog shelter, higher probability of picking a dog than picking a cat. Okay? And if we read this problem more thoroughly, it says a family has 3 kids and each kid will be choosing a pet. Now that's really unusual. That'd be a lot of animals all of a sudden to get at your house, get 3 new animals. Are these dependent or independent? How can you tell it's independent? Yeah, the 0.57 keeps carrying over. It doesn't matter if you pick a dog or a cat, it's always 0.57 and 0.43. So that means that it is independent. Now, just there is a little bit more of the chart down there, but okay. Now, I want to talk about in the real world, would it depend? I think it would. I think it would really depend, because if you walk into the animal shelter and they only have 1 dog, isn't that going to like change your opinion maybe on whether you're going to take a dog or a cat? Maybe the 1 dog is kind of scary looking, looks like he might bite you or whatever. So all of a sudden, no, okay, a cat will be fine. So it depends on a lot of things. Or what if you were trying to decide between a dog and a cat and then both your siblings picked dogs? And then you're like, well, then there's already going to be 2 dogs, so maybe I'll pick a cat. All right. Okay, back to, that's just a real world difference between independent and dependent. In this problem, it says it's going to be independent. But in the real world, it would probably be dependent. Next, it says draw a tree diagram. Cool, tree diagram's already done, and these are a pain to make. If I just asked you to draw it, usually kids would be way more sloppy, and it would take 15 minutes to draw. So I don't want to wait. I got the tree already here, and we're going to have you make only a couple trees on tonight's homework, because I know they're a pain in the butt to make. But once you have the tree diagram, it can answer lots of cool questions. This first one is super easy without having to do anything on paper. Can you see which route it is that has all 3 kids choosing a dog? So you just go 0.57 times 0.57 times 0.57, or even smarter, 0.57 to the 3rd, right? And you would get that, 0.185, okay? So, next one. What's probability exactly 2 of the kids choose dogs? All right, that's a little harder. You still don't need your iPad open, but you could use a calculator. If you've got a calculator separate from your iPad, that'd be awesome. If you have to use the iPad's calculator, go ahead. But I don't want you anywhere except the calculator right now then. Exactly 2 kids choose dogs. You've got to ask yourself, which of these routes work? This route up at the top, that does not work because it's all dogs. And it said exactly 2, not 3. This route works though, because it was a dog, and a cat. So that one is one of them. Once you figure out what that is there any other way you could get 2 dogs? Yeah. You could do this one. This. So that way works. How about this? Wait, I got to use a new color now. How about green? Cat, dog. All 3 of those routes work. Figure out the final answer. Put it in your calculator. Don't just sit there, please. Get the feeling some of you are not typing. I need to get an answer from all of you. Okay, now would you please open up the response app on your iPad and send me what you think the answer is? I'm going to pause for a second while I take a look at those answers coming in. Okay, I was getting almost everybody saying 0.419, and 0.419 is correct. Okay, good. Now, we haven't done anything new yet. So where's the new stuff? This is still not new. What's the probability that the kids will choose at most one cat? You got to parse through the words and carefully. At most one cat. Like, does this one right here have at most one cat? Yeah, because at most one cat just means you can't have more than one cat. These guys don't have more than one cat because they have all dogs. That way it works. So at most one cat's going to be a bunch of things. In fact, not all of them at all, but that one works, at most one cat. This one works, that has at most one cat. This one has at most one cat, the one that goes here. And that's it. What would you do with all of those? Add them all up. Okay, good enough. Let's get the idea on that. This is where it starts to get to be more of a challenge. Okay, so now, this is the part where I need to remind you what probability really is what you want over what's possible. Here's an easy one. What's the probability of getting all three dogs? Well, then that's this, this, and this, and technically you just multiply them all together, or 0.57 to the third power. Do you get that? How is this ever dividing? Because everything was possible in the original problem, and then it's just probability that all three are dogs. So all of these added up were possible, and they were always adding up to what? 1. And therefore, did you ever have to divide by 1? No, because it was only adding up to 1, and then dividing by 1 doesn't do anything. But on all those previous problems, technically, I should have made you divide by 1. It just seems really dumb because it doesn't do anything. Why are you dividing by 1? Because everything was possible, and everything adds up to 1. Now, do you get where I'm going with this? Not everything is possible now. Given that the first kid chooses a cat, do you get not everything is possible? Some of these over here are not going to be possible. They're not allowed. They're not in the possible range here. So what I'm trying to figure out is what should be possible. Given that the first kid chooses a cat, first kid choosing a cat is right here, do you get that only this part of the chart right here is even possible anymore, and the rest of it, I can't use those numbers anymore? Because given that the first kid chose a cat forces me to have only these things possible. And if I added up this plus this plus this plus this, those numbers I would get, all of those numbers add up to this. That's the fast way to do it. It's true. If you actually get all those numbers, they add up to 0.43. And take a wild guess what all of these numbers would add up to. 0.57. Okay, so all the things that are possible now is not 1. It's not all of them added up. It's 0.43. Those are the things that are possible because we know that the first kid chooses a cat. So we know only these things are possible. All right. Now, which of them do I want? Because that's going to go on top. What's the probability? All of the kids choosing cats. Okay. That's cat, cat, cat. So why can't I just do 0.43 to the third power? Because the first step was already chosen for me. So I have to divide by what was possible. Not everything was possible. These couldn't happen. So I had to divide by 0.43. Now, if you think about that, isn't 0.4 to the third over 0.43 to the third over 0.43, isn't that the same as 0.43 to the second power? Yes, it is. And here's another way to think about it. This part already happened. So it's only these two that are left. Does that make sense? That's another way to do it. But I want you to do this over the possible thing because that's the way it's going to work on all the problems. If you, from now on, whenever you see a given question, you always divide by what's possible and you change the denominator to something and divide by the right thing, you'll get these hard ones right. All right, this next one could make your brain explode, so I'm going to not do the next one. I'm going to jump to, all right, well, let's try this one. What is the probability that the kids will choose at least one cat? Did I say any given? Were there any conditions on this? No. It's just a simple question. They will choose at least one cat. All right. They're going to choose at least one cat. Then, does this work? No. Does that work? Don't pretty much all the rest of them have at least one cat? So do you really want to have to do all 7 of these things, or would you like to know a faster way? All right, the faster way is, instead of doing all 7 of those and adding them up, do you get what all of them would add up to? What do they all add up to? 1, and then just take away the top one, this one, the one we can't have. So I go 1 minus that times that times that. You know what I'm saying? If you don't like that way, then go ahead. Add up that plus that plus that plus that plus that plus that plus that. It'll take you 10 times as long. Instead, just take 1 minus the one we don't want. 1 minus that times that times that. 0.57 to the third. Okay. I don't want to do that one right now. I want to show you one more tree. And this time, I'll pause while I get this ready. Okay, I found a good problem. This one is about boys and girls being born. And according to this, boys are a 49% chance, girls are a 51% chance. And this is about having 3 births. This is the first birth here. The second birth is in between those 2 lines, and the third birth is this set here. Okay? And then I've got it all summed up really nicely here. This is boy, 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 and that's the probability of it. Boy, boy, girl, there's the probability of it, etc. And by what you know about these things, do you get all of those should add up to what? 1. All right, so then, tell me this. If I say given that the first child's gonna be a boy, if I know that, because they had 3 kids in their family, and I know the first one's a boy, but I don't know the other 2. Given first boy, what's the probability of boy, boy, boy? The most common mistake people make is they say, oh, boy, boy, boy is right there, 0.17, 117. Do you get why that's wrong? Because it was given something. So what do I have to have? A fraction, and what I want on top and what is possible on the bottom. And what I want is the 0.117. But what was possible? Not everything. Because it was given that at first it was a boy, all of these were the only things possible. And so I could add up all of them, or I could be smart and say what? 0.49. Do you get that? Because I said given the first kid was a boy, that changed this from a 1 to a 0.49, because that's the only things possible. And then what I wanted was the boy, 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 so it's 0.117 on top. Okay. One more question about this one. And I want you to do this completely yourself. You can use your iPad, your calculator, and then submit your answer through the response app that I made, the instant response. Okay, ready? Given first child is a girl, what's the probability of exactly 2 girls? In other words, it's not okay to have 3 girls. You win if they get exactly 2 girls. Given the first child's a girl, what's the probability of exactly 2 girls? Remember, it's a given problem. Make one of these. Okay, pause for a second while you're working on that, and then I'll check your instant response answers. Remember, type it in the response app when you're done. You got your final answer. Okay, so here's how you do it. You say what is possible is only if the first child is a girl, and so therefore it's this part of the chart, and therefore the things that are possible, 0.51. You could add up this plus this plus this plus this. Then what I want is to have exactly 2 girls. That's this one and that one are exactly 2 girls. This one doesn't count because it's got too many girls. It's only supposed to have 2. All right, so then you got 0.127 plus 0.127. Okay. Final answer, 0.498. All right. One last kind, but I actually would like to take the time to actually start your homework with you. And we'll get to it as the last part of problem 1. Problem 1 has like A, B, C, D or whatever. So right now, find your homework. And problem 1 uses this exact chart. It's about boys and girls. And I'll work through it with you as we get closer to lunchtime here. Got about 1 more minute. So everybody get your homework open. Nope. That's going to be Mondays. Today's is called Conditional Probability. If you look at the day it was assigned on, that's the easiest way to do it. It was assigned on 9/13. Doesn't it say that in the title, I hope? Okay. Okay. We're soon at lunch, so like 30 more seconds. It's called Tree Diagrams Conditional or something like that. It's the one assigned on 9/13. And the very first question, if you got the right one, is going to be talking about boys and girls, just like my chart here does. Okay. Would you read me, Mr. SS, read me number 1. Very first question of it. Not all the directions, but just like find the probability of.
What is the probability of all 3 children being girls?
All 3 being girls, that's easy. It's right there. Boom. Right? That's all there is to it. If you have a nice chart made, those kind of questions are easy. Okay? Read me the next one.
What is the probability that exactly 2 of the children are boys?
2 are boys. All right. Which of these work? Now remember, technically, that was 0.133 divided by 1 because you're dividing by everything could work. The next ones are, which was it? What was it again? Sorry. 2 boys. Where's 2 boys? There's a one with 2 boys. There's one with 2 boys. There's one with 2 boys. Does it say exactly 2 boys or at least 2 boys? Ah, so then this one can't work. All right, so those 3, and what do I do with them? Add them all up and technically divide by 1 because everything was possible. All right, we'll finish this up after lunch. Okay. All right, so here we are back from lunch in the middle of the first problem. It was like were we on C, I think? I just did B. Okay, so part C. Would you read part C, back corner? Big shirt. C as in cannibal. 1C. At most 1 girl. At most 1 girl. Okay, so does that mean that they could have girl, girl, girl? No, that one's out. Girl, girl, boy, that's too many girls. Too many girls. Here's at most 1 girl. Too many girls. Here's at most 1 girl. That works. And how about boy, boy, boy? Is that at most 1 girl? Yeah, that works. Okay, all of those added together then. And remember, technically divided by 1. That won't matter until we have a given. And then we'll be dividing by something else. Okay, KL, would you please read me the next one? Stop. As soon as they said given, first child is a girl, that changes my what? What part changes? If it's a given. I have to have a denominator. All right, if given the first child is a girl, I have to have a denominator now. Now the denominator is all of those things are what is possible. And so given the first child is a girl means the denominator, all of these added up to what? Come on, 0.51, good. There we go. So there's the denominator. That's what it's possible. And then, what's the other part of the question then? Okay, and that's where, here's girl, 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 and it seems like it should have just been 0.133 and that would have been it. But why is it divided by this? Because only these things were possible, and you could divide by your possible, and all these added together add up to 0.51, so we put it down there. There's your answer. You got to just divide it. Okay. Next one, KL, could you read me one more? Wait. Given what? Okay, stop. Right there, I got to do some bunch of work to find out the denominator. Given the at least one's a boy? Is that what you said? Okay. Does this work? Does that work? At least one's a boy. At least one, at least one, at least one, at least one. Wait a minute. Only that one doesn't work. So you can either add up all the ones with the arrows, or, remember this? You do one, and then what's the one we don't want? That one. So you could say all of this should add up to 1, so we could instead go 1 minus this one. Okay, so 1 minus 0.133. If you'd rather just keep on adding up the things that work, you could just add all of these up, and it will be the exact same thing as 1 minus this one. Okay, and then how about the top? Now continue reading the last part of the question. All 3 being boys. Well, that's easy. Again, 3 being boys is right there. 117. It's the key, though, is the denominator. It's what you got to divide by. Okay. Was that the last one of this, from this question? So, there'll be one more question I want to help you with, and it has to do with seeds germinating. And here's the thing, it even confused me when I first read it. It said there's 3 seeds that are germinating or not germinating. And I thought, okay, so I go like this. There's not 3 things that could happen. There's 2 things that can happen when you plant a seed. It'll either germinate or not. And then how do I do the second seed? Over here. Germinate or not. And how do I do the third seed? Germinate or not, germinate or not, germinate or not, germinate or not. Okay, that's how you're going to do the one with that has 3 seeds. Because they either germinate or they don't. You can't, like, there's not 3 things at the beginning. And then there's one of a couple bags of marbles kids get confused about. There's 2 separate bags of marbles. If it says they're equally likely to be picked, do you get that there's bag 1 and there's bag 2? And then they're equally likely means 50-50. That's how you start that chart. You could pick from either bag. Your first branch is either a 50-50 because they said they're equally likely. And then you have to do the rest of it. Be careful. Make your charts really nice. Ours was so easy to work with because it was all clean and neat. And so take the time to make a nice chart and you'll be able to get these right. It's really what it comes down to. If your chart's so messy you can't read it, then you really have a hard job to try to answer the questions. So make nice trees. Problems become easier. Okay. This was a tougher lesson today, but it seemed like you guys followed me pretty well. Nice work. And that's all I got for the recording for today.